All right, guys, let's get to 4.4 here. This direct proof and counter example. I forgot to write example here. Okay. So this one will be mainly doing proofs with divisibility. So just like last time, we had to have a definition, we have to have a theorem, and then we can start proving things. So first is let's break down the definition of what it means to be divisible. That's going to be the entire section pretty much. So if n and d are integers, then n is divisible by d. If and only if, so there's a double directional arrow that we did in logic. N equals d times some integer, and d cannot be 0. So different ways we can write divisible. Just a quick note here. Instead of n is divisible by d, we can say that n is a multiple of d. So that's one way you can write it. Another thing you could say is d is a factor of n, or d is a divisor of n, or d divides n. See, all these are all the same thing technically. Also, mention this notation we're going to be using. The notation d is like a straight line n. D divides n. That's what that means. D divides n. Symbolically, if n or d are integers, so this is how we write the definition of division or divisibility using our mathematical symbols. D divides n if and only if, right, there exists an integer, say in k, such that n is equal to d times k. So that means, so if something divides into n, that means you can write n as this divisor times some multiple k. Also, if you see this in the book, d does not divide n, is what this means. Okay, so it's just like not equals, just a line through it. All right, so let's do a couple of basic questions. So let's use the definition. Is 21 divisible by 3? Well, that's the same thing as saying what? Let's use our definition here. So divisible by 3, that is the same as saying 3 divides 21, right? Which means by definition that there exists a number k that's equal to 3, or d in this case, times k. So that's the same, that would mean that there is some multiple, which we know is going to be 7, right? So yes, because it can be written based on a definition. Let me write this a little better. One moment. A little more proper. So 3 divides, just use the arrow. That means that 21 is equal to 3 times some multiple. That's how we should be saying it. Sorry about that. Okay, B. Let's do does 5 divide 40? All right, so the one that divides into is the first one. So you would say, does 5 divide 40? Well, can I write it as something times 5? Right, that would be simply 40 would be equal to 5 times 8. So yes. I'm going to put a check mark for yes, it works. Because I'm out of space. So this first example and first few problems in your homework are just going to be testing you. Can you see the difference on the wording, right? 21 divisible by 3 means 3 divides 21. Does 5 divide 40? Yeah, it's the same thing. Okay. Let's do a different one here. Is 32 a multiple of -16? Okay, remember we said that's the same thing as saying, right, up here at the top, multiple. Same thing as saying, is -16, does that divide 32? It's the same question. I'll write it down here. So that means, right, using the definition, that 32 is equal to -16 times some multiple, right? So the only multiple that I could choose here to make it positive 32 has to be a -2. So yes, the answer is yes. Anyway, so all these, first example is just learning how to apply a definition, right? Knowing that division means you can rewrite it as something times a divisor, something times a divisor. Now let's go to another example. I forgot to mention a quick note here. This might be some confusion. A divides B means, right, B over A technically. It means it goes in evenly. It's not, well, I shouldn't say these are equal, but it means that B is dividing A, but it is actually divisible. So what I want you to remember is that do not confuse A divided by B, right? A divides B means if this is 4 and this is 2, 2 goes into 4 evenly. That's what that means. This means like 4 over 5 or something, just a fraction, or 4 divided by 5. It doesn't mean it's guaranteed to divide into it. So don't confuse this. Okay. So let's do another example here. Just wanted to make sure I mentioned that. Example 4.4.3, divisibility and algebraic expressions. Okay, part A. If A and B are integers, is 3A plus 3B divisible by 3? Well, we can kind of see why, right? So the answer would be yes, and you would say, you would show why. Yes, because 3A plus 3B can be written as a multiple times A plus B. So we know A plus B are integers, so this is just some integer, right? Who cares? Integer, oops, misspelled that. So 3 would divide into 3. So no big deal. So you have some basic questions at the beginning like this. Maybe let's do another one. If K and M are integers, is 10km divisible by 5? Well, 10 km can be rewritten as 5 times 2 times k times m, right? So since 5 divides 5 times 2 times k times m, then 10 km is divisible by 5. So no big deal. We're just explaining ourselves, trying to be more proper. Well, let's do another. Let's do something different. Let's check something that does not divide. Okay, so example 4.4.4. Checking non-divisibility. Does 4 divide 15? I should write that better. One moment. Does 4 divide 15? By definition, the answer is no, right? Because if we, by definition, let's write that. If 4 divides 15, then it can be written as, and then 15 can be written as 4 times some factor that equals 15, right? Some integer, I should say. But there is no integer k that makes this true. Therefore, 4 does not divide into 15. Oh, sorry about that, wasn't on the camera. And more simply, right? So that's one technical, almost like a proof there. But if we write it this way, 15 over 4 is 3.75. So no, an alternate way to say it. No, 15 is equal to this. Therefore, 4 does not divide 15. Right? All right, let's look at some more examples. Okay, let's do a proof here. Transitivity of divisibility. So prove that all integers a, b, and c, proof for all of these guys. If a divides b and b divides c, then a divides c. So transitivity, right? So this is visible into this one, and this goes into that one, then this one also goes into this one. So just using the definition, it should come right out. So since if a divides b, then that means you can write let's go ahead and write it all at the same time, make it easier. Since a divides b and b divides c, then we can say then b is equal to a times some constant we'll call, I don't know, I think the book uses r. And C is equal to B times, let's say, S. We want to show that A divides C if these are true. That is to say that C is equal to A times, I don't know, let's use T, I guess. Okay. All right, so let's look at this. Let's see, one moment. Make it easier. Let's make this equation 1 and 2 just to keep our head straight. So because of 1, right, I can rewrite B. So C is equal to B times S, which would be equal to A times R times S by equation 1. If you notice that, I'm just substituting B in here. And now there's an A factor here, so that would be equal to A times R times S. And this means that C is not divisible by A, right? Because it's right there. So since C is equal to A times R times S, where R times S is some integer, then A divides C. So that shows what we wanted to show. Okay, so basically we use this fact, we apply a definition of division on this guy. That gives us this. And I'm gonna make a little note here. R and S are integers, by the way. And T is an integer, of course. We said that, but I'm gonna make it best to write it down. So B is equal to AR and C is equal to BS based on the definition applied to these two. So now I can substitute the B, AR here. So C is equal to ARS, where R times S is just some integer. And once we change it back into going the other direction, using the definition, if you can write A times some multiple, and that's equal to C, then that means that A divides C. That's a proof of transitivity of divisibility. All right, let's try doing a proof by counter, or I guess not really a proof, but if they ask you to prove this and it turns out to be false, then you either prove it or show a counterexample to disprove it. Okay, because in order for a statement to be false, all you need is one example. For something like this, for all integers A and B, so it's saying that all integers, the following is true. So if you find one integer or one example that this is not true, then you're good. Okay. So if A and B, if A divides B and B divides A, then A is equal to B. So it's saying that if A goes into B and B goes into A, then A must be equal to B. Okay, so let's try to think. So apparently it's false. There's no way to prove that, but if you tried to prove it, you're going to see it wouldn't make any sense. So the counterexample is a little easier to do. So just think of some numbers here that'll see if it's true. So in the book, they say let A equal to 2 and B equal to -2, right? Then then -2 is equal to -1 times 2, and 2 is equal to -1 times -2. Right, so this is a true statement, right? -2 is equal to this times that, and there's my A and B. So therefore, or thus, I guess, thus, A divides B and B divides A, right? But notice that A is not equal to B. So check it out. So A is 2 and B is -2. So 2 goes into -2, no problem. -2 goes into 2, no problem, right? And here is the definitions, writing them as using the definition of divisibilities right here. But honestly, you can kind of see it straight up. 2 goes into -2, -2 goes into 2. They're not equal. Therefore, this statement is false. Therefore, the statement is false. Okay. Given any integer is a new definition greater than 1, the standard factored form of n is an expression of this form. So n, if it can be factored, it will equal to some prime p1 to the power of e1 times p2 to the e2, p3 to the e3, all the way to pk to the ek. So this is where k is a positive integer, and p1 through pk are just some prime numbers. Who cares? E1 through ek are positive integers, so there's just some number, some powers. Although all the p's are in ascending order. Okay, p1, p2, p3 are all smaller than each other. So let's practice writing 3300 in a standard form. So 3300, using the factor definition here. Let's start small. We know that's 33, for sure. We know it's 33 hundreds, right? So 33 times 100. And I know that 33 is technically 3 times 11, and 100 is 10 times 10. So that would be 3 times 11 times 2 times 5 times 2 times 5, right? Break down the 10 all into prime numbers. But now the standard form requires that they're all in descending order or ascending. So the 2's first, the 3, the 5's, and the 11. So I'll just put them in order. I haven't done any math yet. So this will be 2 to the second times 3 to the first times 5 to the second times 11. So that's what I mean by factoring to standard form. That's the first example. There are a few problems like that in the homework, which will help the divisibility problems. Let's do another one.